Okay, let's try again. Welcome to the Calc 2 exam review thing. I'll probably go like over there, I'd say. Yeah, I'll just do it. Well, you guys are over here, I guess I'll do it over here. Okay. So, welcome everybody. I said there's more people who said they couldn't make it than who could make it in person, so I'm definitely going to record it. Perhaps a different medium would be superior to this one, but we'll decide that for next time. Okay, so two people who are here have you get to go first. Can't think of the word. So yeah, priority. There you go. So you got anything you'd like to go over?
I have one thing. There was a problem from, I think, homework.
Okay.
Can we show you it?
Sure, please do. However you want to do it. You're right up here if you got it.
Okay. That was a problem.
Okay. Did you see the recitation session recording by chance?
I didn't go to that. I had another class during the time. So
Okay, sure.
Did someone choose that?
Yeah, someone chose
Okay.
one very similar to this one. So I'll go through it quickly.
Okay.
But if you want more elaboration and detail, you can watch that. Yeah.
Okay. No
So here we go. So the trick is this is almost a polynomial, right? It's a polynomial over another one. And one good strat to handling problems like this is to take the one that can be expanded and expand it all the way out, right? So you can calculate that x minus 1 cubed, which of course means x minus 1 times x minus 1 times x minus 1. That works out to be x cubed minus 3x squared plus 3x minus 1. So this can actually be rewritten as, first of all, we can pull that 3 out. And we can write it like this. I'm going to make sure that that's all inside. Yep, sure is. Looks great. Okay. I would love it if this thing were not in my way, but I don't want to put it up there either, because that would be kind of rude. There we go. Okay. So, right, so now that it's in this format, we can split it up like this. I guess I'll just keep going over here. We can split it up like this. So this is a whole big polynomial over just a monomial. Which means you can write each one as its own thing, right? This is the fact about fractions, And if they all have the same denominator, you can write them all as one like that, or you can split them up like this, and that is equivalent. So this is the same as that, right? All these different things over x squared separately. And so then, now that it's written this way, each of these we can simplify quite a bit. Right, x cubed divided by x squared, that's just x. How about this term?
3.
Right, that's just 3. How about this term?
3 over x.
That's right, and then nothing really you can do with the last one.
Yeah. That one is, can you change it to ln, or is that later? I mean, differentiate it.
So yeah, so all of these we can do with the power rule or the ln. Right, so it's this one whose integral is the natural log, right? So yeah, so just as a reminder, 1 over x, or x to the negative 1, the antiderivative of that, right? So if this arrow, I use this arrow to mean the derivative, the antiderivative of that is ln. But besides that one, we use the power rule on all of them, so like x to the negative 2, right? The power rule says you increase the power by 1, and then you divide by the new power, which is -1. So in this case, it would be negative x to the minus 1. Right? So that's relevant for this last one here. So anyway, so we'll go through all these. This is
Thanks.
oh, was that locked?
Yeah.
Okay. Well, that's, yeah. Good. Okay, so yeah, so this is that. This is that. That. And that. So x, goes to x squared, and then you divide by the new power. X to the 0 goes to x to the 1, and then you divide by the new power, which is 1, so it's just 3x. This is the special one where you can't use the power rule, it's the natural log instead, or 1 over x would be the natural log, so 3 over x is 3 times that. And then this is x to the -2, so like I saw here, you end up with negative x to the -1, but since it was already negative, a positive x to the -1. And if you prefer to write that like this, that's just as well, right? X to the -1. Then finally, we just plug in all those things and then work it out, which I'll probably stop there, right? Yeah, okay,
Thank you.
you're welcome. So yeah, so trick is expand that out and then you simplify it and then it's power rule after that.
Okay.
Right. Okay, do you have one that you'd like to go over?
No, I don't have one to go over.
Okay, how about you?
Pretty much any of the integration by like parts.
Integration by parts.
Yeah, that's kind of where I'm like, I get lost after a certain point, depending on the problem. I don't have one in like specific. Actually, maybe I do.
Yeah, that'd be great because it's really quite a wide class of.
Yeah. There's actually one he did in class.
So is this the integration by parts formula that you guys have learned?
Yeah.
Okay.
Was it the two-step one that you did, or the
Yeah, I think it was the. I'm trying to find it. I have it.
to the x times cos?
It wasn't that. That one did. Yeah. So e to the x times cosine dx.
Okay, so that one is a wacky, really funky one among all the integration by parts questions. So if you want to practice integration by parts in general, which some other people requested as well, it would probably be better to do a different one first.
Okay.
And then come to that one later.
I think that's the only one he did yesterday.
I think you did one more. It was just x cos x dx.
Oh yeah, x times cosine x dx. Yeah.
Perfect. Right. So this is going to be a good, you know what, actually, I'm going to be real colorful with this. Let's do it right here. Okay, so the integration by parts formula says that if you have a product of two functions, right? So, or no, that's not how it's written first. Right. So you're trying to take the integral of the product of two functions. This is kind of one way that it's written. Right, so u is some function of whatever your variable is, and then v is also another function of whatever your variable is, and dv is supposed to mean the derivative of that. So don't get too caught up in it. It's for when you have a product of two functions and you're trying to integrate that. Right? So the integration by parts formula says, like we talked about last time, unfortunately you can't just distribute the integral over multiplication. You can't just take the integral of each piece and then multiply them back together. Fortunately, it doesn't work like that. But integration by parts is one tool that you can apply to such a situation. It says that you can replace this with, and I already forgot to do what I said I was going to do. That if you have one function and another function like this, right? So it says that you can replace this with u times v, maybe this is a little over the top, minus the integral of v du, right? So it's saying that you can swap out this integral for, some stuff and then a new integral. So effectively, it's a way of exchanging one integral that you have to deal with another integral that you have to deal with. And that's a good idea if it turns out that this new integral is an easier one to handle than the one that you had before. Right? So a perfect example of when you can use this technique is for x cosine x dx. So you're trying to find the antiderivative of not just cosine x, but x times the cosine of x. So let me be clear, right? It's x times the cosine of x, like that. So in order to use this formula, we're going to want to choose how to label this, right? So we're going to have to consider some part of this, the u, and another part of it, the dv. And then what we're going to do is we're going to end up swapping the whatever we chose as u, that's going to be replaced with its derivative, du. And whatever we chose for dv, that's going to be replaced by its antiderivative, v. So in this case, we pretty much have two choices. We can say, let this be u, and then let all this other stuff dv. We always want the differentials to match up, so the dx would be included in the dv, and this would not. So if we're doing that, we're saying u is x, and dv is cosine x dx. Well, then that would mean that when we make the swap, du would be just 1, or just dx. And v, if we go up a derivative, so take the antiderivative here, that would be sine of x. So the formula tells us that we can swap this integral of u dv for this integral, right? So we'd be swapping the integral of x cosine x dx with this integral, which is just sine of x dx. That's a good trade, right? Because we lost this x. So that is a good idea. Let's do it. Now don't forget about this part, right? That's kind of the leftover part of using this formula, right? So we're going to have u times v first. So that's u times v first minus our new integral, which is v du. So that's just sine of x dx. So there we have it, right? So just to be clear, this is our new v. And here's u. This is our du, right? So we swap this u dv for this new integral v du. And in this case, with this choice of u and v, that was a good idea. And so now I can continue on and take this integral, no problem. Yes?
Why does du become dx?
Great question. So let me say something briefly about calculus notation, right? Unfortunately, it's a real mess. Unfortunately, the same notions of calculus were kind of invented in like 2 or 3 or 4 different places by different people, all about at the same time. And so there's a bunch of conflicting notation systems that might seem to kind of not really fit together and not really be like a well thought out notation system. That's because it's not. So, yeah. So with that said, when we're using this formula, we use this notion of the derivative. The derivative is this little d. And when you apply the d to things, it just becomes the d whatever, right? Unless it's a more complicated function, then yeah, then v just becomes dv, and sine of x would become d sine of x, which is equal to cosine of x dx. So that's just kind of like how it works. It's just we're trying to capture this thing in the universe with a system of chicken scratches and how to use symbols to do stuff, and this is just the rules for the chicken scratches.
Oh.
And it turns out it works out to capture that thing in the universe, you know? So yeah, so that might be a kind of disappointing answer, but
I understand.
that's all I can really tell you. Yeah. You can get into more of the philosophy of like describing it this way or whatever. It might be more familiar to say, to rewrite this equation, rather than writing it as du equals dx, you could write it as du dx equals 1, right? Take this and divide it over to that side. So you get du dx equals 1, which might be more familiar from here, right? The derivative of this with respect to x, well, that's the derivative of that with respect to x, and that's the derivative of that with respect to x, you know? So this is just another way of looking at this, the same kind of thing. So, yeah. Okay, so here we are. So we should be in good shape now because this integral is easy. The integral of sine, or the antiderivative of sine, is negative cosine, but since it was already negative, that's going to make it positive cosine. So there you go. So allegedly, using the integration by parts formula, we have come upon the alleged fact that the antiderivative of x times the cosine of x, its antiderivative is x times the sine of x plus cosine of x. And then of course plus, 7 or whatever you want at the end, right? Plus c. So let's actually check if that's really true, right? Well, let's take the derivative of this. First, we're going to need the product rule. So I'll take the derivative of this one and leave that one alone, and then leave this one alone and take the derivative of that one, and then this one, the derivative of cosine is negative sine, and then the c goes to 0. And then you can see that this term and this term and this term are all 0. And so you really do get x cosine of x. So yes, this really is the antiderivative of this, right? And it was pretty hard to see that, if you were just going to sit here and think through, like trying to guess and check and come up with like, okay, what would work? Maybe you'd eventually come up with that, but it'd be kind of hard to find, right? It'd be kind of hard to find, that's for sure. So the integration by parts formula allows you to swap this integral for another, and then get the antiderivative out of that. Okay. So yeah. So that's how. Oh, so darn. So what I should say is it all came down to our choice of u and dv. All right. Let me show you what could have happened if we had made another choice. What if I had chosen to make this my u, and then the other stuff, right, x dx to be my dv. Right, that's also a valid way you could say, either way, you're just saying this is the product of two things, and that's the product of two things. So there's multiple ways to look at it as the product of two things. So if we look at it this way, then here's what results. Well, dv is x dx, then v is 1/2 x squared. And if u is cosine of x, well then du is negative sine x dx. And so if we just follow that same formula with this naming of u and v, then it says this is equal to u times v, so 1/2 x squared times the cosine of x. All right, actually, you know what? I should just leave it in the same order, just for clarity. U times v minus the integral of v du. And again, why would I do that when I'm trying to illustrate? Du. All right, so if we swap it this way, This is u. And this is du. And this is v. So this is another 100% correct, valid way of using the integration by parts formula. That is, so this integral is not only equal to the expression and integral we had before, but it's also equally well equal to this expression and integral that we have now. Both of those maneuvers are totally valid. You can let u and dv be whatever you want as long as you use the integral, the formula properly. That's totally legit. But that sucks though, because this integral is even worse than the one that we had before, right? This was a totally not the move. We swapped integral with a x to the 1 times a trig function, and now it's x to the 2 times a trig function. So that's even worse than what we had before. So totally valid, but not useful, because it doesn't get us any closer to a solution. So that's usually how it goes with integration by parts. That one choice of u and v, all choices of u and v are valid, but one choice of u and v might get you to an easier integral, and other choices of u and v might get you to a harder integral. So that's kind of what it's all about, is making the right choices so that the things get simpler when you make the swap compared to harder. So yeah. Okay. Any more integration by parts that you guys want to do? Besides the one that you mentioned.
I think these are the only ones that he went over in class with us. That I actually have written down.
There's one question I have though.
Okay,
I
perfect.
have nothing. It's literally.
I was gonna ask about that one too. Yeah.
I see. Okay. Okay. All right. I'm trying to look at what some of the other students requested.
Yeah. If you want to take theirs first.
Yeah, I think I want to stick to integration by parts for a minute.
Yeah.
How did you guys feel about the partial fractions?
Where's that?
Do you have that?
Are you talking to us or them?
Yeah, talking to you.
Oh.
There's nobody on here. This is not one.
Oh.
Yeah. Do you have that or no?
I don't think we went over that.
Good.
Yeah, I think he just went over last class Fundamental Theorem of Calculus, substitutions, and then integration by parts.
Yeah, you only did those 3 things.
And I think he said improper integrals or whatever, those are off the test. I don't know about partial fractions though.
Okay, great. All right. Well, one person asked about those. Hold on, that's a different class. Integration by parts. All right, I'm doing integration by parts for that person. And this person asked for the integral of that. Okay, so we'll do that next. Okay, so let me do, let me look up some good problems. With somebody, thank you.
Sorry.
Yeah, you're
So break up.
How's it going so far?
Challenge.
Okay, let's go with,
So we just went over problem yesterday. We just went over problem yesterday.
all right, let's go with another example here. How about, t squared times e to the 4t dt. So we got 2 things going on here, right? Again, you can see it's the product of 2 functions, right? It's a second degree monomial, and then a exponential, right? And so let's think for a moment about how the derivatives of these things work, right? The monomial works like this. Works like this, right? That if you go up in the derivatives, oh no, that's not it. 1/3 t cubed. If you go up in the derivatives, it becomes a higher degree monomial. If you go further in the derivatives, it becomes a constant and then 0. Right, so that's what's up with that one. What's up with this one? Well, this one, if you take the derivative, it gains a 4, but it otherwise stays the same. And in fact, if you do it again, it'll gain another 4, but it will otherwise stay the same. And then if you go backwards, it's going to be losing 4s, right? You're going to be dividing by 4 if you go the other way. Right? So the behaviors of the chains of derivatives of these two functions are quite different. This one is getting simpler as you take derivatives and more complicated as you take antiderivatives. This one is staying pretty much the same no matter which direction you go. Right? So, notice what we're doing here, the integration by parts. We're picking one piece to exchange for its derivative, and we're picking another piece to exchange for its antiderivative. So which of these two functions do you think would be wise to choose to be u, and which one would be wise to choose to be dv?
Yeah, choose e for dv. Since the derivative doesn't really, because it changes to become the derivative, it wouldn't it stays the same basically.
The dv becomes its antiderivative. Right? We start with dv and then it becomes whatever its antiderivative was. But you're absolutely right anyway that the antiderivative is not any worse. Mm-hmm. Right? Yeah. So then, why is it a good idea to have the other part be the derivative then?
Because we just said it's simpler as it goes, as we find the derivative, and it's harder when you get the antiderivative.
Exactly. So it would be a very smart move to let this be the u, and let this be the dv. Because when we make the swap, this is going to be replaced with this, which is at least a bit easier. And this is going to be replaced with this, which is not any worse, right? The fact that this has a constant, this has a constant, no problem, right? The constants are super easy to handle, so we don't really have to even look at that. The main part of it is what we need to worry about. So this says this is equal to rather, u times v. So u times v, right? That's u times v. To be a little better, I'm gonna do it this way. So u times v minus the integral of v du, right? So v du, so 1/4 e to the 4t du. Okay. So this works out to be 1/4 t squared e to the 4t. That is outside of the integral, so we no longer have to worry about that. That's just a residue from what we were doing. This is the part that we have to keep thinking about. Are we able to handle this now? So I can at least pull these constants out, right? 1/4 times 2 of the half. And what's left on the inside is a t, and then e to the 4t. So, as usual, we've exchanged one integral for a new integral. Was this a good trade, would you say? Is this new integral better than the one that we had before? Do you know the antiderivative of that, now that you're looking at it? T times e to the 4t. Yeah? What is it?
Yeah, but we have to get rid of t, then e to the 4t is just e to the 4t.
Right. So we're not there yet. So what should we do? What should we do to get rid of the t?
Do it again.
Do it again. Exactly. So observe that by doing this process of integration by parts, we managed to take the power of t down by 1, And so unfortunately, we're still not capable of taking the antiderivative at this point, but no problem, we can simply do the same maneuver. Yes?
Real quick, where'd the t squared go in the beginning? T squared times 1 before the integral. Yes.
Here?
Yeah.
So this was, so this is following the formula here, so this was u
Mm-hmm.
v, and then v du, and so then this term, I just simply rewrote it in a different order.
Oh, I didn't even see the.
Yeah, so 1/4 t squared to the 4t,
Okay.
and then I did the same thing over here, just rewrote it in a different order.
Okay.
Yeah. So integration by parts, you can see you can swap it out, and it seems like you're going to end up, you know, doing the same situation. So we're going to do the same thing again. So this time, u is going to be, so this is a different u and v that I'm setting up for a different application of this formula. I'm saying let u be this, and let dv be this. And then we should be able to work this out. In fact, just to be clear, let me actually do this over here instead. So this formula here, the integral of t e to the 4t dt, we're going to work that out separately. So again, it's a good idea to let this be the u and let this be the dv, because then this one you have to take the antiderivative, but it won't get any worse. And this one you have to take the derivative, and it will get better. Right? So this time when we make the swap, it's minus u times, it's u times v minus the integral of v du. Aha! Now we are at a spot that we can actually take that antiderivative. What are you guys thinking so far? Is this making sense or not really? Sort of.
I'm good right now.
So integration by parts once, we managed to get from here to an expression involving this new integral. But that new integral is still, I can't on site tell you what that is, so I gotta try using integration by parts again on that new integral. And this time, we're in a good spot because, let me simplify this out. This is 1/4 t e to the 4t, and then this is, well, the antiderivative of that. In fact, it's right over here, isn't it? Right, if you go up here and then you do that again, right, it would just be dividing by 4 again. So it's just going to be minus 1/16 e to the 4t plus c. Boom, so there you go. So that's there's no more integrals left, right? We've done all the actual calculus. And so that's the expression for this. So we can replace this integral with that. And then just simplify. So I'll distribute that 1/2 through here. And then remember the whole thing about c, right? It's just, plus some number at the end. And so if you give it a times whatever or whatever, it's still just some number at the end. So you can just relabel it as plus c or whatever. So there you go. So that's the answer. And some people like to do this. Since these all have an e to the 4t in them, some people like to write it like that. And that's totally.
I'm sorry, can you go to the second line? I'm still like lost as to how you got the, so, oh, yep, that one. Yeah, I'm confused as how did that become that, like, on the above one.
So is this good?
Yeah, that's good.
And so then how is this the same as this?
Yeah, well, basically, like, what did you move around and, like, why? That's what I'm trying
Well,
to...
so all I did is I just put these things in a different order. I just put the 1/4 first, and then the t squared, and then the 4t.
Yeah. And then you move the e squared, yeah.
Is that good?
Yeah.
And there's no real reason I did that. That's just like an aesthetic preference on like to have the constants and then.
For example, what happened to the 2t that was the du?
So I just moved things around here as well. So the e to the 4t is here.
Yep.
The t is here. Yep. And then the 1/4 and the 2 both pull those out of the integral.
Yeah.
And then that's 2/4 up front. Yeah. Yeah. So just moving multiplication around. So sometimes you do got to do integration by parts twice, right? Sometimes you'll notice that you do integration by parts, and what you have is something that you don't know how to take the antiderivative of, but it is something that is closer to something you know how to take the antiderivative of. So if you just do that a couple more times, then you'll finally get to the end. Okay. All right. So with that. And so doing what we did here over here, I recommend at least imagining this in your mind, like what's going on with the derivative of this one or that one. And so then you like strategically decide which one you want to take the derivative of and which one you want to take the antiderivative of. And since this one's getting simpler this way, you're going to want to go this one. You know? Okay.
Can you still like do this one? So because I'm still copying it, or
What'd you say?
if you're gonna move on to the next question, can you still leave this one?
Oh, sure. Okay. Yeah, I have plenty of room over here. Okay. Yeah, that's fine. Okay, so, well, I guess you can't see over here, so I'm going to like here, right?
Yeah, I can see it.
Okay. All right, so I'll start over on the left half here. So here's the situation. Somebody asked about this function. Is that the one? You in the blue?
Oh, sorry. Yeah, that was it.
Okay. So so how do you take the integral of something like this? So, now that you have this thing in your tool belt, it should look, that should trigger you, the fact that it's a product of two different things that you know about the derivatives and antiderivatives of, should trigger you to think of integration by parts. So again, you'll have to make the choice of one of them to be u and the other one to be du. So let's take a look at what either choice will be like. Let's say we were to have, so e to the x and cosine of x, right? So if we let e to the x be u, then we're going to be taking its derivative, and we're going to be getting stuff like e to the x, e to the x forever, right? Even if we do multiple applications of integration by parts, we're just going to be going further down this chain, and it's going to be the same the whole time. In fact, the same is true in the opposite direction. Its antiderivatives are also all e to the x. So it really doesn't matter whether we let this one be u or dv. There's no advantage either way. It stays exactly the same complicatedness in both directions, no matter how far you go. So yeah. Cosine of x is a little bit different, but not really. Its antiderivatives are different from it, but still like the exact same complexity level. It's not more or less complicated than it was, right? And same thing in both directions, really. And no matter how far you go. So both of these functions are kind of tied for u and v. It really doesn't matter which one you let be the u and which one you let be the dv, because you're just going to end up with the same kind of thing. So let's give this a go. So if we try to use integration by parts here, let's just say I'll let this be u, and I'll let this be dv. So that means, so if dv is cosine of x, well, that means v is sine of x. And if u is e to the x, well, so let me just put it another way for a moment. That means du dx is e to the x, but in this context, we express that in this slightly different way. Du equals e to the x dx. Right? So yeah, okay, so now we can make the swap. We want u times v. U times v minus the integral of v du. So v du is actually going to be that. Right, and just to be clear, that's u times, I gotta do this in both hands here. U times v minus the integral of v du. Right? So that's what I get after making that swap. Does that make sense? Everybody on the same page? Okay. Are you good with copying that one?
Oh yeah, yeah.
Okay, sweet. So now let's take a step back and observe what we have accomplished. We have managed to replace this integral, the original one that we started with, e to the x times the cosine of x. We've managed to swap that out for a new integral, e to the x times sine of x. Now, unlike this example where we managed to swap it out for a new thing which was better than what we had, clearly it was a this part stayed the same complexity, but this part went down in complexity, so that was an accomplishment. But here it looks like this was almost pointless because this stayed the same complexity and this stayed the same complexity. So we have almost the same integral, so it's like, what was even the point of that? But this is a really funky one. So it may seem like all hope is lost, like this technique cannot accomplish what you are trying to do, but it actually can. We just go one step more, and then you will see it is pretty wild. So let's now, whoops, probably shouldn't have done that, that's okay. Let's write it again. Yeah, so let's do it again on this integral. So let's do that same thing again. So e to the x sine of x dx, right? So let's try and use integration by parts on that. And I'll make the same exact choice. I'll say that will be my u, and this will be my dv. Okay, so then same situation. U is this, du is this, dv is this, and that means v is this. You got to be very careful with the signs in this. Positives, negatives in this problem. Okay, so we can say this is equal to u times v, e to the x times negative cosine x. Sorry, that's my mistake there. So differentials always go together, right? Du should be blah 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 dx, dv should be blah 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 dx. This should not have a dx, right? The derivative of something without a dx does have a dx. At least that's the way the notation works in this context, which, like I said, is a whole jumbled soup of different inventors' notations all put together, so it's kind of a mess. But, yeah. Okay, so, anyway, that's u times v minus the integral of v du. So that's v du. So in other words, we get negative e to the x cosine x, and then this negative can come out. And so again, this might have been what one would expect. We just get back to an integral with e to the x cosine x. And so at first thought you might be like, and this is certainly what I first thought when I first tried this type of thing, was like, well, that was completely pointless because I just got back to the same one that I started with. I just went around in a circle. There's no way I can gain anything from this. But check it out. This we can rewrite now. This says, let me get rid of these things now. This says the integral of e to the x cosine x dx is equal to e to the x sine of x minus this integral, which we just got an expression for. It's negative e to the x cosine x plus the integral of e to the x cosine x dx. And if I simplify that, distribute this negative, so after all of that, what I have managed to do is write, I do not have, I still not done. I haven't gotten an expression for this integral that doesn't also have an integral in it. So it's like I still just have one integral in terms of another. But this time I have an integral in terms of itself. It's the same integral on both sides. This and this, the same integral on both sides. In fact, that's what I'm looking for. And in fact, if it were plus here, then it would just cancel out from both sides. But it's not. It's minus. So what I could do is I could add it to both sides of the equation. Let me get rid of this line. I don't mean division. I observe that it's on both sides and it's on negative on that side, so I'm going to add it to both sides of the equation here. And so it's going to become 2 times, so let me shift over here a little bit, 2 times the integral that we're looking for is equal to these 2 terms, which do not involve an integral. And then what do you know? I've pretty much got it here, don't I? Boom, boom, done, right? So what's crazy about this is we never actually got to a point where like we did with the other problems where we're like, aha, now I know what the antiderivative of that is, so I can just do the integral. We never actually did the integral. We never actually got to the end where we're like, okay, I know what that is, no problem. That never happened, and yet we still did the integral in a funny way. We ended up with an expression for the thing. And of course, you better pop on one of those. But yeah, so that's the funny thing that you can do with integration by parts, where you sort of go through these cycles. You say, I'll take the derivative of that one and the integral of that one. But then when you go around twice, you've actually got the negative of what you had, and then you can just pop that over there and then divide by 2 and done. So yeah, so a pretty crazy technique. I think that is pretty cool. It's a real funky application of integration by parts. Okay. So I think that's all I have to say about integration by parts. Does anybody have a question about that or about another thing? There's one more question that I'd like to attend to from somebody who's not here. Anybody else? Okay. All right, then here we go.
He said one thing yesterday. He was talking about one thing we will need to know how to do is, I think he said, he was talking about the impartial fractions or whatever, dividing by arctan or something. That's like the only thing he mentioned.
key. Oh yeah. Well, I think that's actually going to come up in this problem.
Okay.
So, let's talk about partial fractions for a second. So if I give you something, so first of all, let me just compare it to fracting, right? If I give you something like this, there's a quick process you can do to figure out, what's the expanded form of that, right? You just FOIL everything together, you combine like terms, then you get a thing, right? Let's say, though, I give you this and then ask you to go backwards, right? That can still be done, but it's more difficult. You have to think about, okay, what are all the things that multiply to 15 and add to 2, right? So it's like more, here you just follow a step-by-step process, but going backwards, you kind of have to like guess and check through a whole list of possibilities. So going backwards is harder than going forwards, but you can go both ways, right? So this is very similar. Hello, Russell. Sorry, this is John. You called me. Oh, okay. Yes. I left the balcony door open. So if you could go around the back and walk up the staircase and open up the door. Okay, yes, I have done that. All right, bye-bye, thank you. Okay, so putting things like this together, right? So there's a straightforward algebra algorithm you can do to put these things together, right? You have to give them both a common denominator. So this term we have to give it an x minus 4 in the denominator, and this term we have to give it a x plus 3 in the denominator. And then once we've done that, then they both have the same denominator of whatever the product of those is, which I suppose I can work out would be x squared minus x plus 12, x squared plus x minus 12. And now that they have the same denominator, you can simply combine them together. 5x plus 8. Right, so there's no, you just got to follow this algorithm basically, right? Just multiply by whatever to give them to match their denominators together, and then you just go on from there, right?
Is it plus x or minus x in the second denominator?
Yeah, you're totally right. Thank you. That is minus x there. Yes, and sure it ought to be, because the whole point is that they're supposed to have exactly the same denominator. So yes, absolutely. Thank you. Right. Okay. So again, though, let me ask you the same question. You think it could go backwards, right? In fact, here's the trick. If you see something like this, which is a large fractional expression, or a rational expression, they call it, where it's a polynomial over another polynomial. If you observe that this denominator factors as x plus 3 times x minus 4, then it's actually guaranteed that there's some way to split it up as the sum of two partial fractions, where those denominators are the factors of this denominator. So guaranteed there are some two numbers, a and b, which when you figure out what they are, this is actually exactly equal to that, right? But the trick is to figure out exactly what they are. Right? So the way you figure out what they are, we already know that they're 1 and 4, but let me just show you. So it's 5x plus 8. And of course, the whole thing is that you've observed that the denominator actually factors as x plus 3 times x minus 4. Well, the way you figure out what the correct choice of A and B is you just take this, you multiply both sides by this denominator, so it completely cancels out on this side. On this side, this is being multiplied by x plus 3 and also x minus 4, so the x plus 3's cancel out, and you just get this. And this one's also being multiplied by both of those, and so the x minus 4's cancel out, and instead you get this. And then what have you learned to do from here?
Like apply to A and the B, like so it would be ax minus 4.
Okay.
Instead of B, so bx plus 3b.
Okay. And then what? You have learned about this already, right?
What is it? What is the thing?
This is called partial fraction decomposition. Is this a familiar thing that I'm reviewing, or are you hearing about this for the first time?
I'm hearing this for the first time.
You too?
Yeah. Yeah.
Really?
I remember, I feel like we did this in Calc 1.
Yeah, but I don't think we touched it in class in this one.
Yeah.
That's wild. Okay, so one student asked me to, she said it was from homework 4. So,
And did they show you the topics, the test one topics? Well, just actually, it's not the 4, it's the 3. So it's Fundamental Theorem of Calculus, substitution, and integral methods.
oh, okay.
Yeah.
Okay,
I don't know
so,
where she got that from.
yeah,
I
I
don't know.
Okay, well,
I think she or whoever, they mentioned it to the professor, but he was like, I don't even know really what he said, but he said,
Words were not really.
yeah,
That was his answer, so I don't.
but he also said no homeworks 1 through 5, and if that was on number 4, then.
alright, so the point is, you can figure out, you can get a system of equations for A and B, and then you can figure out that A and B have to be 1 and 4, is the point. So, okay, so for this student, I guess I will, come back to this one and maybe record it separately, since this is not for the test tomorrow. Yes.
I was gonna say, and then for this one, did you like, for example, the one that's a plus b equals 9? Did you just like multiply that by 3 for everything, and then you subtract them? Is that how you would solve it? I don't know if that makes sense.
Yeah, that's a great way to do it. There's actually many different techniques.
Okay, that's how I would approach it. But
to
yeah.
solve this, but that is one fantastic way to do it. You could take, so yeah, so
A plus
this,
b, the whole equation multiplied by 3, so it's 3a, 3b equals 15. Yeah, and then you put that, and it would be minus. And so b cancels out.
exactly. So if we subtract these, 3 minus negative 4a, and 15 minus 8.
So a is equal to 1, and then you replace a for one of these.
That's right. So if a is equal to 1 and a plus b equals 5, well then 1 plus b equals 5, so b equals 4.
Okay.
So yeah, so it is possible, so the point is from here, it is possible to recover what these numerators need to be to make this happen, right? It turns out that you can write it as the sum of these two smaller fractions, these two partial fractions is the idea, and it turns out you can do it like that, right? It's easy to check forward, you just give them the same denominator and whatever. It's hard to figure out backward. You have to do kind of a lot of work to figure it out backward, but it can be done. Much like factoring, right? You can do it easy one way, hard the other way, but it can be done both ways, right? So yeah, so why is this useful? Why is this useful? Because,
Yeah, thanks.
oh, that's my bad, dude.
No, that's fine. I got it. Sorry.
It's also recorded, it'll be on YouTube. So
Oh, awesome. Okay. Good.
It's 'cause, why is this useful? Because let's say I asked you that. Good luck, right? But let's say I asked you this. Boom, easy. That's natural log of x plus 3. And that's 4 natural log of, 4 natural log of x minus 4 plus c. Boom, easy peasy, right? So if you see it this way, you know, oh, geez, I have no clue, right? But if you rewrite it, well, then it becomes easy. Because integration is so friendly to things that are added together, as opposed to things which are all jumbled up inside of one big thing, you know? So yeah. Okay. So yes, so you know who you are? I'll come back to this one, the one that you asked specifically. So does anybody have more questions from this, from those 4 topics that,
Could we cover one that, I don't have a question right now, but could we cover one where the way to solve it would be Fundamental Theorem of Calculus? And specifically
yeah, somebody asked me one that I totally didn't go back to. Who was it? Was it you?
It was me, but I don't know if it was fundamental theory.
The reason I'm asking is, I don't know if we talked about this, but the way the test is going to be is that he does he would prefer it if we describe what we're doing, right? So if we have a question and we put on the side to do it by parts, for example. So for example, if you have a question and then you put on the side okay, the way I'm going to do this would be integration by parts, right? And then you do integration by parts because that's how he's kind of going to grade it. It's more as of the approach. And so one thing that he said was not only should you put FTC to say that you're doing Fundamental Theorem of Calculus, but he would also if we put, for example, part 1, part 2. Does that make sense? So that's why. Since that could help in the test.
Gotcha. Honestly,
Yeah.
this is just my personal opinion.
Yeah.
The distinction between part 1 and part 2 of the Fundamental Theorem of Calculus strikes me as kind of stupid to pay attention to. In my opinion, in my conception of calculus, the Fundamental Theorem of Calculus is that derivatives and integrals undo each other. If you do the integral first and then you do the derivative, that's the same as doing nothing, and vice versa the other way. So, but the vice versa the other way is broken up as part 1 and part 2. I don't remember or care which one is which. I'm pretty sure I'm going to be grading the exams, so if it's a Fundamental Theorem of Calculus, you can just say that.
Oh, did not know that. Okay.
If you
I
did
thought
not-
you know you grade. I thought it was.
I think, I'm honestly not sure.
Okay,
I'm
okay.
honestly not sure. So yeah, so if you want to look up which one's part 1 and part 2, you can. I don't
Okay.
know. And
Yeah,
it doesn't
that's what he
actually
said, but yeah.
Yeah.
Okay.
Okay, so let's talk about this one. So this is a funky one. Yeah, go ahead.
Okay.
Thank you. So they're saying define this function of x, call it g. Right? So g of x is this thing here. So for example, so g is a function where you plug in a number x. So for example, you could plug in the number 4, right? What would g of 4 be? Well, it would be the integral from 0 to 16 of e to the negative t squared plus t dt. Right? So notice that the input variable to this function changes the upper bound of this, right? So I have no clue what that looks like. E to the negative t, let me take a look on a computer just so that I can draw it faithfully. Come on, buddy. Wow, that's kind of wild. So it turns out it looks like this. Turns out this thing here. You do not need to know this, but just to help us visualize what the hell's going on, I'm just going to draw it, and I want to draw it accurately rather than draw a random curve. But you don't need to know what the curve looks like to answer this problem. So this is saying the integral from 0 to 16. So it's saying take the area under the curve between there and there. And then the total amount of area, whatever that amount of area is, let me ask the computer. What? I can't do that? It does. There we go. Turns out that area is 1.73. So g of 4. So g of 4 is 1.73. Right? So g is a function that takes in this number x and spits out some other number called g of x, right? Now it so happens that the way it comes up with its number is it takes an integral of this function, e to the negative t squared plus t, takes it from 0 to whatever x squared was, and then spits out that area, spits out the number at the end. Right? So yeah, so, okay. So what they're asking us is what is g prime? What is g prime? So the trick to this, so one way to figure this out would be to figure out what the antiderivative of that is. Write that down, so whatever the antiderivative of that is, write that down from 0 to x squared. And then plug those things in, and then now we finally have an expression, just a regular, normal algebra expression of x. And then that's our function g, and then we just take the derivative of that. Easy peasy. The problem is, what is the antiderivative of that? Does anybody know?
It's the same thing, isn't it? Right?
I'm afraid not. If it was e to the t, the antiderivative would certainly be e to the t.
Oh.
But the derivative of something like this is not itself, because of the chain rule, right? The outer layer would be just that, but then you have to multiply by this other stuff.
Is this a class?
This is a TA session. I'll be done shortly. And then another class is starting at 3:30. No problem. So yeah, so because it's like this is not its own derivative and not its own antiderivative, right? So it's quite hard to figure out what is the antiderivative of that. Right? It's quite hard to figure it out. Here's a great thing. We can actually bypass having to figure it out. Let's just call it something. I'm just going to give this a name, capital F, right? I don't know what it is, I don't know how it works, but I do know that its derivative is e to the negative t squared plus t, right? That's the idea. So then we can actually do the strategy that I suggested without needing to figure out what the actual expression for this is, right? So here we go. So what is g of x? G prime of x, right? Well, okay, first of all, let's work this out. So the integral of this thing is going to be its antiderivative, which I don't know what it is. I'm just going to call it that for a minute. From 0 to x squared, right? So this is still g of x equals this, right? This antiderivative, whatever it may be, from 0 to x squared. So that's, if we plug those in, that's f of x squared minus f of 0. Right. So here we have it. So I've just rewritten the expression for g, but instead of using this integral symbol, I've just made up this name of a function f, and I'm just going to write it like that. Right? Yeah. So I don't know what f is, but I do know it's the antiderivative of that. And now check it out. They're asking, what is g prime? So they want us to take the derivative of this. They want us to take the derivative of this. Well, here's where we're using the Fundamental Theorem of Calculus. The idea that, well, look, we took the antiderivative here, right? Well, you know, f, I made up f to be the function whose derivative is e to the negative t squared plus t. And now you're asking me to take its derivative. Well, no problem, okay? There's one difference, though, that it's not just x on the inside, it's x squared. Right? So we'll have to use the chain rule, right? The derivative of this, well, that's just a change of symbol. That doesn't change anything. But the derivative of this, well, it's just going to be that, but where you've plugged in x squared instead, so that's going to be x squared squared plus x squared, and then times the derivative of that. Right? So that's the chain rule, right? If the derivative of this is this, well then the derivative of this with a thing plugged in is going to be that with a thing plugged in times the derivative of that thing that you plugged in. Right? So that's how the chain rule works. So this is e to the negative x to the 4 plus x squared times 2x. Right? This is the derivative of that. And then minus f of 0. So let's talk about f of 0 for a second. You know, f was supposed to be the antiderivative of that function. I don't know what the antiderivative of that function is. And this is what you get when you plug 0 into that function. And so I don't know what that is either. But I do know that it's just some number. And so when I take the derivative, it's 0. So again, I don't even need to care what that actually becomes, because no matter what f was, and I have no idea, I just know it's this thing's antiderivative, no matter what that is, and no matter what you get when you plug in 0, maybe you get 1.79. Okay, the derivative of 1.79 is 0. So I don't need to know what that is. It's just gone. So you have it. That is the expression for g prime. So so this is g, and this is g prime. Despite not being able to take the integral of this, we actually don't need to. And that should kind of make sense because we're being asked to take the derivative. And so in a way, it's like having to take this derivative and having to take this integral cancel each other out. And so it just works out like that. So yeah. So I strongly recommend this way of thinking about it. Of you just give a temporary made-up name to this antiderivative, and then when you work it out, it's going to turn out that you don't even need to know what it was. So it's just a temporary made-up name that can help you do the chicken scratches to get the answer.
My thing where I got lost from him is he did like basically the same as you, except he used h, and then I don't know like where the 2x came from. So like how fx squared, like how did that 2x? Can you clarify one more time?
Sure. So let me just do perhaps a more familiar example. Let's say this is cosine of x cubed. Right. Recall that the derivative of that. So it's so it's one function plugged into another function, right? The chain rule says that to take the derivative of such a thing,
Oh yeah.
you simply do the derivative of the outer function with the same thing plugged in, but then you have to multiply by the derivative of that inside thing, you know? And so that's what's happening here, you know? If it was just f of x, its derivative would be this, so it's going to be that with this thing plugged in. So it's going to be this with x squared plugged in, but then you have to multiply by the derivative of that thing that was on the inside.
Okay.
So yeah. So the fact that it's x squared in there does make a difference on the rate of change of the function and all that stuff, and that's how that difference comes in. So yeah. Okay. Any last minute questions I can help you with? All right. Then that's that, and I'm going to quickly go over the partial fractions one that one student wanted, which I guess is not on the exam. So, yeah, so you can stay for that if you like, or you can go if you're not interested in that. Thank you all for coming, or
Yeah.
I'll say thank you all for coming in a couple minutes.
I'm not worried about that now, but thank you.
Alright.
Appreciate all the help.
All right.
How do we find the YouTube videos?
I will send it on Canvas in like an hour or two.
Thank you.
You're welcome. Bye-bye. All right. So. Thank you. You're very welcome. So we're trying to find the integral of this thing. All right, here you go. So, yeah, very welcome. Thank you. So the trick to this is to factor the denominator, right? So the denominator factors like this, but then you can't factor it anymore, right? Because x squared plus 3 is unfactorable. That is a quadratic which cannot be factored any further, right? So that's all you can do with that. So you can hope that that there is a way to rewrite this as. We're trying to rewrite, I probably shouldn't have erased that whole thing. We're trying to rewrite this as something over x plus something over x squared plus 3, right? Those are the irreducible factors of that denominator. Now, unfortunately, right, this one is just, some constant over that one because it's a nice first degree factor. But unfortunately, when you're left with a second degree factor, you have to do something kind of strange. It's not guaranteed for it to just be a constant up top. It's guaranteed for it to at least be a first degree polynomial up top. So you can say something times x plus something, and that's guaranteed to cover what you're looking for. So let's see if we can figure out what those are. So again, we'll multiply both sides by everything that's here. And so this is going to be a times x squared plus 3. And this is going to be bx plus c times x. So if we distribute everything, this is a times x squared plus 3a plus b times x squared plus c times x. So if these two sides are supposed to be equal, the only way that can happen is if the x squared terms are equal. So if this ax squared and this bx squared add up to be x squared, or in other words, if a and b add up to be 1, right? Ax squared plus bx squared equals 1x squared. That's the same thing as saying a plus b have to add up to be 1. The x terms, so this cx is in fact the only x term here. So that cx has to equal this negative x. So in other words, c has to equal negative 1. So that was easy. And then finally, the constant term, and again there's only one, has got to be 12. So 3a has got to be 12, which means a has got to be 4. And then if I come back here, if a is 4, then that means b has got to be negative 3. So it turns out that this function can be rewritten as 4 over x plus negative 3x minus 1. Right? That's the result of the partial fraction decomposition. And now that we have that, now we can take the integral. Right? We want to take the integral of this. And so no problem. We just have to take the integral of this. Well, I shouldn't say no problem, but yeah. So each of those things. So the integral of 4 over x. And then we also got the integral of this term. So the integral of, I should say, minus 3 times the integral of x over x squared plus 3. And then minus 1 over x squared plus 3. All right, so I've split this up into 3 separate integrals, right? This one, and this one, and this one, right? 3 separate integrals. And that's a good idea because we have to do them all in kind of a different way. This one you should recognize as 4 natural log of x, right? I hope I'm still in frame here. Yeah, no problem. 4 natural log of x. This one is, we can do with a u substitution. So then I'll give this one of these. Right? So now I can rewrite this as as that, right? 1 over u. That's dx, the halves there makes it the same. That's right. So this is 4. This is actually ln of u, and then u is actually x squared plus 3. So there you go. So that's, this integral is 4 ln x. This integral is 3 halves ln x squared plus 3. And then finally we have that last integral over there. And you just, this is one of those ones where you just have to already know what it is. You have to know that the integral of something squared plus x squared is 1 over that thing times the arctan of x over that thing. In our case, this is supposed to be plus 3. So the only a that would work in this, for this to match up with that, is if a was the square root of 3. So it turns out that we're looking at this, right, for this last integral here. Oh, there should definitely be an integral sign here, that's my bad. This is 1 over the square root of 3 times the arctan of x over the square root of 3. Right? So if you just add that in there, let me make sure I've got that right. It's one of those ones that you just got to remember, and sometimes I don't. Yeah, that's right. So 4 natural log of x, 3 halves, that one. And then finally this one is 1 over square root of 3 times the arctan of x over the square root of 3 plus c. And there you have it, right? So the trick to doing this was break it down with partial fractions. You got to do the bx plus c thing because that's a second degree denominator there, and you can't factor that any further, unfortunately. And then yeah, then it splits up into these 3 separate integrals. This was the a, the b, and the c from our partial fractions, more or less. And then yeah, this is just a natural log. This, because it has an x, you can do it with the u substitution. But this one doesn't have an x, so you can't do it with the u substitution, but you can do it with the arctan formula. So there you go. That's how it works out in the end. All right. Hope that was helpful. Good luck on the test, everybody. And I'll see you later. Bye-bye.